Hello, somebody asked me to do a quick video on the bulk modulus. The bulk modulus problem that is given in the practice exam, question 9, is of a copper sphere that's about 10 centimeters in diameter, and then it's put under high pressure, and its diameter shrinks a little bit. And the question is asking you to figure out what is the change in diameter of this sphere caused by the change in pressure. And to solve these kinds of problems, we take an approach that's very similar to the approach we took with Young's modulus. You might recall in Young's modulus what we had is some cable, and you put it under some stress, and as you put it under some stress, then it's stretched by a little bit. The same type of thing is happening here. With the bulk modulus, instead of talking about a length, a change in length for a cable, what we're talking about is a change in volume. Okay, so here's how it goes. We've got some stress. This is what we subject the material to. It's a change in pressure. We go from, about 1 times 10 to the 5th newtons per square meter to 1 times 10 to the 6th newtons per square meter. So we increase the pressure by basically 1 power of 10. So the pressure is 10 times greater in this circumstance here than it was there. And as a result, it's going to be smushed a little bit, and the diameter we would expect gets smaller. So that's captured by this equation here, which is the bulk modulus equation. And here, the bulk modulus is some very large value, some extremely large value times 10 to the 11th, okay? So this is a very large number, and that means that this value of this fraction over this is going to be huge, and this one down below is going to be small because it has to equal 10 to the 11th. So that's the bulk modulus right there. So I'm going to apply a change in pressure by a factor of 10. Okay, so that's 1 order of magnitude. Now down here we have the change in volume over the volume. This number on the bottom in the denominator is going to be very, very small compared to this one up here because it has to equal a bulk modulus of 10 to the 11th. All right. So what we're asked for is to find out what's the change in the diameter. What's the change in diameter of this sphere? So we're going to take it from this down to here, and we're going to increase the pressure from this to this. And we're going to use this equation to figure that out. So when we want to know about the change in diameter, we look at this equation and we think, well, what's closest to telling us the change in diameter? Well, it's probably this thing here, the change in volume. The change in volume is going to tell us something about the change in diameter. And if that approach doesn't help you just by saying, oh, naturally it's got to be the change in volume, let's look at it from another perspective. What are the things that were given in the problem? Well, if this is our equation right here, we're given the bulk modulus. We're told that it's 1.4 times 10 to the 11th. So we got that. So we have it. We're given the change in pressure. Pressure goes from 1.01 times 10 to the 5th to 1.0 times 10 to the 6th. So the pressure goes from here to here. So we've got this. So we got the bulk modulus. We've got the change in pressure. We know the initial diameter. So that means we know the initial volume. So we got pressure, bulk modulus, and volume. The only thing we don't have is the change in volume. Okay? So what we can do is we can rearrange this equation to solve for the change in volume. That's what I've done down here. So I multiply both sides. Let's just start with this equation. I multiply both sides by delta V, change in volume over V, and then I divide both sides by the bulk modulus. So I get something that looks like this. Then I multiply both sides by V, and then I get the change in volume isolated by itself on one side of the equation. And now, as I said before, we can plug in the change in pressure, we can plug in the volume, and we can plug in the bulk modulus. So we got all these things over here. We should be able to calculate the change in volume. So let's get to work on that. Well, the volume of a sphere is 4/3 pi r cubed. Now, this is telling us something in terms of a radius. We're not given a radius, we're given a diameter. And this is a standard type of problem in physics. You got to be careful to divide the diameter by 2 in order to get the radius. So to calculate the volume, what we're going to do is we're going to do 4/3 pi, and instead of the radius, we have the diameter divided by 2. That's this, and we're going to cube that, okay? So 4/3 pi r cubed is the volume of a sphere. We can calculate that there, okay? So that'll be plugged into this down here, all right? We got the bulk modulus, we got the change in pressure, We'll figure that out in a minute. And over here is the change in volume. Okay, so remember, we're working from this equation here, and here's the change in volume. So that's this. It's 4/3 pi r cubed minus 4/3 pi r cubed. I can factor 4/3 pi out in front. This is the radius of the first sphere cubed minus the radius of the second sphere cubed. So this whole thing is the change in the volume. Change in the volume equals change in pressure times the volume divided by the bulk modulus. So what we see in this way of setting it up is that 4/3 pi is appearing on both sides of the equation, so I can cancel that. The other thing that pops up is this idea of getting the radius. It's always a diameter divided by 2, and we're going to cube it in all these cases. All right? And so the diameter divided by 2, if I cube that, that's going to be 2 times 2 times 2, which is 8. So this is going to be d1 cubed divided by 8. This is going to be d2 cubed divided by 8. This is going to be d1 cubed divided by 8. So I can just knock out the little 2 cubed on everything. So when you simplify that equation, it turns out to be something that looks like this. It's the original diameter, quantity cubed, minus the new diameter, quantity cubed, equals this change in pressure divided by the bulk modulus times the original diameter cubed. Now, what we want to do is basically get some change in diameter. Now, I can't really get a change in diameter by just keeping this thing like that. I can't like take a cube root of that. You can't do that. You have to separate terms. So what I'm going to do is try to collect all the terms from D1 on the left-hand side. So that's this and this term. And then I'm going to collect all the D2 terms on the right-hand side of the equation. I want to separate them. So I look at this term, D1 quantity cubed. I look at this, D1 quantity cubed. This is 1 of the D1 cubed, and this is delta P over B times D1 quantity cubed. So if I subtract this amount of D1 cubed from both sides, and then I factor out D1 cubed on outside the parentheses, then I get 1 minus delta P over B. So that's just this minus this stuff with the D1 cubed factored out. And then if I add D2 cubed on both sides, it'll disappear from here and it will pop up over here. And that's where it pops up like that. So I get that. Now what I want to do is I want to isolate D2. So I have to take the cube root to undo this fact that it's raised to the third power. So if I do that, if I take the cube root, I get this, just D2 by itself. If I take the cube root of D1 cubed, I just get D1. And then if I take the cube root of this thing in parentheses, I basically get this thing, you know, with a cube root there of this 1 minus delta P over B. There's a lot of math involved, at least algebraically. You got to do these things. And so that's how I can get D2. And if I can get D2, then I can find the change in diameter between D1 and D2, because I know what the original D1 is. It's just 10 centimeters or 0.1 meters. If I can find D2, I can find the change. So to find the change, I got to get this. Now, I know what D1 is. That's 10 centimeters. I know 1 is. I can calculate delta P. They told us what the two pressures were, and I'm given the bulk modulus. So now let's go ahead and do those. Let's start with delta P. So delta P is here. This is the larger pressure, 1 times 10 to the 6 newtons per square meter. They gave us that. And then this is the atmospheric pressure, 1.01 times 10 to the 5th newtons per square meter. If I subtract these guys, put it into your calculator, you get this, 899,000 newtons per square meter. By the way, a newton per square meter is a Pascal. So this is 899,000 pascals. That's the change in pressure. That's good. I've got this term up here. Now I've got B. That's given to us. That's the bulk modulus. That's a fairly large value, 1.4 times 10 to the 11th. And that's because copper is a fairly stiff material. You got to change the pressure by a huge amount to get any kind of change in volume. So I put delta P over B, delta P over B right there. I've got the numbers in here. And then I evaluate what's in the parentheses. I get 1 minus 6.42 times 10 to the minus 6, okay? I'm going to take the cube root of that. That's what this thing means right here. Okay, so I'm taking the cube root of that. And remember, this was the diameter. This was D1 And when I took the cube root of d1 cubed, I just got d1. See, the original diameter is 0.1 meters. So now I plug this into my calculator and take the cube root of it and multiply it by 0.1, and I end up getting this value, 0.099999786 meters. That's really close to 0.1 meters, okay? Really, really close. And so I take the difference between D1 and D2, I just subtract these guys, and then that ends up being 2.14 times 10 to the minus 7th. That's a really small number. I made a mistake in the original notes. That was 10 to the minus 6th. Somehow I copied it down wrong. But anyway, it is 10 to the minus 7th. And since the answers are not given in meters, but in centimeters, you got to convert. And so what I do is I take 2.14 times 10 to the minus 7th meters and multiply it by 100 centimeters over 1 meter. This number right here is exactly equal to 1. It just has different units. On the top is centimeters, on the bottom is meters. So there are 100 centimeters in 1 meter. These two things are exactly equal. They just have different units. This allows meters on the bottom to cancel and then leaves the only units standing to be centimeters. So when I multiply this by that, I end up getting 2.14 times 10 to the minus 5th centimeters. And that's the correct answer on this problem, is D. So just to summarize, going back, what you have is you get some really stiff material, copper, you put it under increased pressure, and its diameter is going to shrink. How are you going to find that out? You got to use this equation. The bulk modulus is the stress, which is the change in pressure, over the strain, which is the change in volume divided by the original volume. So you just work that through, a lot of little steps. You got to be careful with the calculator and copy things down well all the way. So this is your key equation that you go for right here. Any type of problem like that on the final exam is probably going to use this equation. And you're going to be given certain parts, and you're going to have to find out something that you're not given, okay? And in this case, as we went over, you're given this, you're given this, and you're given this. You're not given this. So calculate the thing that you're not given, the delta V, and then from that, you'll probably be able to answer the question. Hope this is helpful. Leave comments below if you have anything that you didn't understand.